Welcome to class, everybody. You might wonder, why does Mr. Bailey have sunglasses on? It's because I got a concussion. It's because it's Red Ribbon Week, and we're wearing sunglasses to block out drugs or something like that. I always thought it was, I don't know. Concussions seem like it's not a small deal. Like, even if it's just minor, you literally got brain damage. And we're like, yeah, throw some sunglasses on, get back to class. Because football's what's most important, though. Yeah, no, I don't know. But that being said, my favorite sport's bad on concussions too, so I can't trash on football too much. All right, let's see. Let me take this off, and we'll get going. So they're going to start off with, we left off on 7.2 yesterday. They just basically went through like what makes your volcano explosive, what makes it non-explosive. If you increase the temperature, that's going to, if you increase the temperature, that's going to decrease the viscosity. So it's more melted, it flows much easier. You will have a less eruptive or explosive volcano because it's easy for the lava to come out. The same thing with silica. If you increase the silica, you increase the viscosity. So if you have a lower silica content, like a basaltic rock, the magma is going to flow much, much easier and not be explosive. And then your dissolved gases usually do the opposite of what you'd think. My brain, for several reasons, thinks if you have dissolved gas, it should create bubbles. It should I guess dissolved wouldn't be bubbles. It would be like the CO2 in your soda before you open it up. It's not bubbles inside until you open it up. But anyways, your dissolved gases do the opposite of what I would think. I don't know about y'all, but the more dissolved gases you have, the lower your viscosity and the more easier your magma flows, which is probably more like a physics thing. But I don't know. I'll have to look into that. Oh, there it goes. Just took a second. Sorry. I didn't mean to go crazy. So they're going to break down the different types of lava and tell you that 90% of lava is basaltic, meaning it has more iron and more magnesium. It's dark colored, similar to the rocks that we see in the oceanic crust. It flows in thin, broad sheets or ribbons. The flow rate is about 10 to 300 meters per hour, which is not well. That's actually pretty fast. It's faster than I thought it would be. So 10 meters per hour is kind of slow. 300 meters per hour is pretty fast. That's several football fields worth of length in an hour. So it's kind of booking it. Up to 30 kilometers per hour downhill, which is like the speed of a slowly moving car. Basaltic lava can flow pretty quickly because it's less viscous. It's more like a thin honey kind of consistency as opposed to something super thick. About 9% of lava is andesitic or intermediate, meaning that it has a higher content of silica. It's going to be more viscous. And then very little lava, about 1%, is rhyolitic. They have very thick flows that move really, really slow and don't flow beyond a few centimeters or a few kilometers from the vents. So they kind of stay put where they're at. I believe that Oklahoma had some volcanoes that were either rhyolitic or andesitic. They have some nice red volcanic rocks up in Oklahoma, different than the red dirt that we see. But yeah. Did I ever tell y'all about the super slow moving science experiment, like the pitch drop experiment? Yeah. So basically, I must have told his class, but not y'all's classes. This scientist took tar pitch, which is just thick tar that they use to make streets and roofs, and he put it in a funnel at room temperature, and everybody's like, this is a solid, it's not a liquid. And he's like, no, it's a liquid. It's just a really, really, really thick liquid. And so he just left it in this funnel, like under a glass, for years and years and years. And once every couple years, like a drop of it will fall out. And it's people watch it on the internet to see like if they can see the drops fall. But over like 50 years, maybe like 10, 20 drops have fallen out of it. And so it's just like a kind of demonstration that although you think something is solid because it doesn't move very fast, it very well could be a liquid as long as the molecules are moving around in a certain way. So rhyolite is very, very thick and doesn't move very fast at all. So we have two different names for types of lava flows, and these are going to be taken from the Hawaiian Islands, from which the people that live there have always been associated with volcanoes and dealing with volcanoes. So their terms are better than ours. So we have, how would you pronounce double A? Ah. You just pronounce both the A's. This is pronounced and this is pronounced pahoehoe. You do pronounce the E's. Pahoehoe. And so these are the two different types of lava flows that you can have. Pahoehoe is the nice, like, visually stunning lava flows that look all like dramatic and they flow over each other. They describe it as ropey surfaces, and we'll see them in a second. Is like just a rough pile of what looks like torn up street that just gets piled up and is on fire because it's lava. And so if you see like a big mound of what looks like rocks, that's going to be If you see like what you think in your head is like a classic lava flow, that's going to be pahoehoe. And then they do mention there's lava tubes. Basically, the conduit that leads up to the surface that transfers the magma to the surface to become lava. Once the volcano is done, if the magma recedes, so will the magma inside those tubes, and you're left with like these empty tubes, almost like giant wormholes. And you can go inside them and explore around in them in different places as long as the volcano is not active. And like I mentioned at the end of class, we're exploring using tubes like that to live on the moon, because we wouldn't have to dig a shelter or build something extremely ridiculous to protect us from meteorite impact. So here's some pictures. This is the It's nice and blocky. You can see that it's all like piled up, and it just looks like a flaming pile of like dark rocks. So that's the This is the pahoehoe, the really nice looking stuff that like folds over itself and gets the crust on the outside, flows downhill really easily. So this is like the pahoehoe is like the classic lava flow that we always like to see. The is just like a big pile of lava rock. Probably moves a lot slower than the pahoehoe would. Maybe not a lot, but definitely slower than pahoehoe would. And then here's someone standing in a lava tube. So at some point in time, this was filled with lava and it was coming up to the surface, which you got to be like pretty trusting that this volcano is not active, because it's like a movie scene. You see lava like come around the corner behind her and you're like, oh my God, there comes the lava, and you have to run through the tunnel. So yeah, that wouldn't be super great. But I guess they actually have the name of this: Valentine Cave, a lava tube at Lava Beds National Monument in California. So you can go and stand inside a lava tube in California. Nice. So gases in magma are called volatiles. When you think of gases in magma, think of like CO2 in your soda. And so we put the CO2 in the soda because of the pressure. You can't see the gas that's dissolved in the soda until you take the cap off. Once you release the pressure, the gas comes out and it's more visible and you can kind of see it exiting. So gases in magma are about 1% to 2% of the total weight. Most of it is water, which is why I kind of equated volatiles and gases in magma to be water at the very beginning. But we do have carbon dioxide, nitrogen, sulfur dioxide, which is what gives you that like stinky volcanic smell, and minor amounts of chlorine, hydrogen, argon. It does contribute to the atmosphere. Significant quantities can alter global climate. So we've tied not all of them, but some of the hothouse periods to increased volcanic periods. When you have much more plate tectonics, you have many more volcanoes, and they're releasing quite a bit of carbon dioxide and other greenhouse gases into the atmosphere, which is actually opposite of what we thought it would be. We thought that early on, high volcanic times would produce more ash, which would block out the sun and cause global cooling. And it actually turned out to be the opposite because of the carbon dioxide. And actually, they don't do this too often. There's also like a reflecting effect that keeps energy from going out when you have clouds. So sometimes on the weather, you will see that the areas in the morning that don't have any clouds will be colder, and the areas that are covered with clouds in the morning will be warmer because the clouds kind of act as a blanket to trap in some of that heat and keep it from escaping out upward into the atmosphere. So I mentioned the confining pressure. Just like soda, when you have your soda pressurized, that CO2 stays inside. When you release the pressure, it all kind of bubbles up. So as long as you have that confining pressure underneath the surface, the volatiles are going to stay inside and continue to do their thing. So what kind of particles are erupted from volcanoes? We have very specific terms that we use for these. They mentioned this in the videos that we watched yesterday, pyroclastic flow. And so most things that come out of a volcano can be referred to as pyroclastic. The pyro part as like the hot term, meaning used to kind of illustrate the heat of a volcano. And then clastic, just like we talked about clastic sedimentary rocks, that's meant to be like pieces of other things. So hot pieces of your volcano coming out. So we have ash and dust. Hot ash fuses to form welded tuff, and tuff is just like a volcanic rock made out of ash. We have lapilli and cinders are pea to walnut size pyroclasts. We have big ones called blocks, so anything larger than 64 millimeters, which is kind of a random size, but 64 millimeters is what? About 6.5 centimeters, which is roughly like 3.5 inches. So anything over 3.5 inches, we call a block. And then sometimes, it sounds crazy, but you can have a block that gets thrown into the air and the inside is still lava, but the outside is like solid rock because it's cooled. Those are called bombs. So bombs are streamlined blocks ejected while still molten, and then when they hit the ground, they like explode with lava, which sounds kind of like a bomb. So blocks and bombs are about the same size, but one of them has lava inside and the other one's just a lava rock. And then they have two different terms, and we've already seen these in the igneous rock ones. Pumice is your rock that has a lot of holes in it because it's lava that's been exposed at the surface, and those bubbles are created by reactions with the air. Scoria is going to be the exact same thing. It's just a dark colored one. Where pumice is light, scoria is dark, and both of them have the vesicular texture and the holes all in them. So here's just a little chart to show you these. We're not going to do like a volcanic rock lab. That kind of went along with igneous rocks. But we have volcanic ash, which is very, very small, under 2 millimeters in size for the pieces. Then you go up to lapilli or cinders, which is between 2 millimeters and 64 millimeters. A lot of this would probably be, have you ever seen like the red volcanic rock they use for landscaping? You might see it every once in a while. It's not as popular as it used to be, but I've got a little square of it next to my driveway. I didn't put it there. The previous homeowners did. But just like little red, holy, like volcanic rocks. And so those are going to be lapillis. And then you get up into your blocks and bombs. This would be a block, and that would be a bomb. You can see it's cooled now, but you can see that there was like molten lava inside of this thing before it cooled down. So that's maybe like one of the most terrifying things, that a volcano can throw a giant like bomb of lava at you. That would be really scary. So pumice and scoria, pretty much the same thing, but pumice is going to be light colored, scoria is going to be dark colored. Andrew better not be sleeping back there with his sunglasses on. Hear your deep breathing. Okay, what are the three characters of material extruded in a lava eruption? Lava flows, gas, and ash, and then your pyroclastic materials, which also include your ash, lapilli, blocks, and bombs. So, volcanic landforms are the result of many generations of volcanic activity. So when you see a volcano, it doesn't get pushed up that way. It builds up slowly over time, layer after layer after layer after layer. Many eruptions, even if they're small eruptions, to kind of give it that shape. So all volcanoes pretty much start at just like a crack in the ground. There is no mountain, there is no hill. Just the lava pushes, or the magma pushes its way up to the surface, finds a weak point, usually a crack, which we call a fissure, and it starts to flow out onto the surface and builds the base of what will eventually be a large volcanic mountain. So the flow is localized into a circular conduit. It kind of melts out the area of the crack and makes it more conforming to allow it to flow out. So you get this nice conduit. We use the term conduit today to like run electrical lines. It's like the metal pipe you run your electrical lines in, or I guess PVC. But in volcanic terms, this is going to be like the lava tube in a way. Lava tubes are conduit. It's what takes your magma from below the surface and brings it to the surface where it comes out on the surface. The conduit terminates at the vent. The vent is the actual place right where it comes out from below ground to the surface. And then successive eruptions form a volcanic cone. I was hoping they would have. Here we go. So see how all of this is built up when you kind of slice into it. You see that it's layer after layer after layer, and a volcanic mountain of this size would have taken several hundred probably smaller eruptions to kind of build up this shape, where the first eruption would have just been flat along the surface of the earth. It kind of would have just spread out, but it doesn't always spread very far from where your conduit is and where your neck is. And so the first one kind of builds the base. The next one builds up, and they slowly start to form this hill. And when it's a small eruption, it doesn't really get off the hill. You can see it kind of coming down, but it's going to solidify a lot of this lava on the actual hill surface, which is going to help build it up and make it more and more dramatic of a cone. So a couple more terms. I did go back, right? Yes. A couple more terms. Your crater, we're all familiar with the volcanic crater. That's the little indent at the top where your magma is kind of receded in between eruptions. And so you have this depression at the summit at the very top where ultimately the lava will kind of come out. It's formed by erosion during or collapse following the eruptions. Calderas are going to be giant craters, and we'll talk about calderas when we talk about much larger volcanoes and their kind of life cycle. Flank eruptions generate parasitic cones. So by flank, they mean like on the side. And if I have a weakness somewhere on my volcano where the lava is not going to come out of the top, it finds a crack and pushes its way out the side. That's going to form like a secondary little volcanic cone on the side. And they call it parasitic because it's kind of like pulling lava and magma from the main volcano. And then secondary vents, which are going to be like flank volcanoes, but no lava, just gas, that emit gas only, are called fumaroles, like fumes. And I don't know the rolls part, but fumaroles makes me think of like smoke coming out somewhere. Didn't go for it. There we go. So this has a couple of those. You have your magma chamber underneath. This is what's feeding your volcano and causing it to happen. The pressure builds up. It pushes the lava up. Initially, just a fracture in the ground. It's not this nice round-shaped conduit to begin with. It's just a fissure in the ground. And so the lava comes up, spews out onto the surface. Where your lava actually comes out onto the surface, it's much higher now, is called the vent. At the very, very beginning, down here at the surface, it would have been right here. But now as the mountain, the volcanic cone goes higher and higher and higher, your vent goes higher. Lava coming out the side is going to form like a parasitic cone. So you have like a mini little volcano on the side of your larger volcano. The stuff that's shot into the air is going to be your pyroclastic material. It can be either ash, bombs, or smaller size pieces, lapillis or cinders, all of those different terms. And then you have your actual lava flow, and they don't have a fumarole, but if you had like gas leaking out the side of a volcano, that would be your fumarole. So yeah, conduit, neck, pyroclastic material. This is a nice little picture. And I guess we don't have a lab on this. If we did have a lab, I'd give you this picture and you'd have to label it. So what are the basic features of a typical volcanic cone? Conduit is the neck that feeds the magma up to the surface. Your vent is where it comes out. Your volcanic cone is the actual volcano itself, the shape of the mountain that the volcano forms. The crater is at the top where the vent is. It just kind of sinks down a little bit in between eruptions. And then your parasitic cone and fumaroles are little vents on the side that can either leak lava or just gas. Now, different types of volcanoes. Shield volcanoes is where we're going to start off with. These are the very, very large ones. And their example of a shield volcano is going to be Mauna Loa in Hawaii. Mauna Loa is the largest shield volcano. It's also the largest mountain on Earth. If measured, you got to have a little parentheses there. If measured from the bottom, from basically base to peak, the problem with Mauna Loa is most of it is underwater because you're actually measuring from the seafloor. And so if you measure from the seafloor from Mauna Loa, it is much taller than like Mount Everest. But we only get the very tip of it that's exposed above the ocean floor because it's an island of Hawaii. So Mauna Loa is, you can see on the image here, maybe if you can kind of make this out. Mauna Loa is in the center of the main island of Hawaii, the island of Hawaii. Kilauea, which we talked about the other day, that's been erupting since 1983. That's over here off to the side, and they have several other volcanoes on the main island. So remember, this main island right now is directly beneath the hotspot, so it's constantly getting fed new volcanic material. So they're pretty active volcanoes on that island. But it's about 9 kilometers high, very low angle, so you can see that it's not like a very steep mountain. It wouldn't be difficult to climb to the top. It would just take you a long time because you have a far horizontal distance to cover. It does have a well-developed caldera, and we mentioned a caldera is a crater that's much, much bigger. I believe the cutoff is like 1 kilometer. So if your caldera is 1 kilometer in diameter, or if your crater is 1 kilometer in diameter, it will be called a caldera. A well-developed caldera from collapse of magma chamber following eruption. So basically what they're saying is the eruption happens, your magma chamber kind of spins itself, and so it gets emptied out. And once you have this emptied out hole with not much pressure inside of it, the stuff on top of it kind of collapses down. Even if it's just partial, it leaves a really big crater underneath. Let me go back to the last page and make sure I didn't miss anything. So shield volcanoes, broad dome structure built by accumulation of basaltic lava. Most begin as seamounts. A seamount is an underwater volcano. If it never gets to the surface and comes above the water to be an island, it will always be called a seamount. But an underwater volcano is a seamount. So Canary Islands are one. The Hawaiian Islands, Galapagos Islands, which, does anybody know where the Galapagos Islands are? I didn't know till yesterday. I was looking at plate tectonics and I saw the Galapagos Ridge. The Galapagos Islands is in the Pacific to the west of like the southern part of Mexico. No, I guess it would be the northern part of South America. And so that's just really interesting. I've always heard of like the Galapagos Islands and never like knew exactly where they were at. So also Easter Island, Newberry volcano in Oregon. What? The Newberry volcano in Oregon was a seamount? I'll have to look that up. Easter Island's out near New Zealand, right? That's the one with the like statues that were buried. Yeah, Easter Island. Okay, so that's a shield volcano. No, when they say shield volcano, think of Hawaii and Mauna Loa being the tallest volcano or the tallest mountain on Earth if you measure from the seafloor. So, Kilauea is the most active and studied volcano. It's been erupting since 1983. It's had 50 different eruptions since 1823. The magma chamber inflates and earthquake swarms indicate an impending eruption. So it's pretty active. And even when it's not active, it has nice warning signs to tell you that it's about to go off. Where are we at here? I think we're moving along pretty good here. So here is a size comparison with the different types of volcanoes, which we haven't gotten to the other two yet, but we can go ahead and show you the size comparison. So this is a shield volcano. You can see the overall size, especially if you go down to sea level, and just how wide and broad it is in a diameter sense. This would be a composite volcano like Mount Rainier, Mount St. Helens, Mount Fuji, just the classic volcano that you think of on land. And then this is a tiny cinder cone volcano. You can see lots of these in Arizona. Arizona, New Mexico area actually had like a failed continental rift. North America tried to rip itself apart. And there's a lot of these little cinder cone volcanoes there that you can see. And you can hike these like in less than a day. They're pretty cool looking. So, what are the characteristics of a shield volcano? Broad domes built by many basaltic flows just over and over again. They spread out really far, so your dome is really, really wide and not very steep at all because in general, the lava is going to flow really well. Now, you get to your cinder cones, and this is a great name. It's really cone-shaped, and it's mostly just cinder. Not a lot of lava flow. There is some. But a lot of pyroclastic materials come out and just build up over and over again. So they're very symmetrical. They're nice and round, pleasing to the eye. Steep-sided, so it's not like one of the gently sloping shield volcanoes. It's nice and steep. Loose accumulations of ejected scoria, so like your pyroclastic material as opposed to like your nice flowing lava. It does have lava flows, but not all the time and not super common. So pea to walnut-sized fragments, mostly basaltic. They'll be dark-colored, reddish to brown color. Some produce lava flows, and the craters are relatively large and deep. And here's a picture of one. And so this is a nice cinder cone volcano. I mean, look at it. It looks nice and round, like you took a funnel on the beach and made like a little beach volcano, which is a weird thing to say, but I think it's accurate. You can see this one did have some lava flows. You can definitely see the area that had lava flow on it and the area that didn't. But in general, this is just a bunch of ash, like a giant pile of ash that's just built up over time from many, many flows. What do they have down there? As a flow, I can't read that. At an flow emanating from the base of a cone, buried much of the village in San Jose. I can't read that. Having only remnants of the village's church. Para-agriculture, San Jose, para-agriculture. That's so weird. But yeah, so you can see that this flow just kind of covered this entire town, and you can only see like the top part of the church left. So yeah, they're small in size, although this one looks like a decent sized little hill here. But they're saying like 30 to 300 meters for your cinder cones. And so definitely something that you could hike up in a day. You know, you come up here, I don't know, you get all the way to the crater. And you want to be careful because probably a lot of loose material. But if you ever get a chance to visit a little cinder cone volcano, go and check it out. They're pretty cool. Here's another picture of a cinder cone. This one definitely looks a little bit smaller. You can see the trees over here. And so, you know, it erupts and the little pyroclastic materials come out and they just build up and build up and build up. Most of them have that nice round shape, very funnel-like. This one did have a lava flow that kind of came out one side, but they don't usually produce like a whole bunch of lava. What are the characteristics of cinder cones? Small, very symmetrical, steep sides, and usually dark color basaltic flows that come out. Now, composite cone or stratovolcanoes. These are the classic volcanoes that we think of. You can call them stratovolcanoes. Composite cones is a little bit harder to remember, but if you think of their cone just being like built up over time, many layers, that kind of fits in with the composite cone kind of terminology. So these are the volcanoes that are very eruptive. They're located around the Ring of Fire, where you have subduction of your oceanic plate, of your Pacific oceanic plate, underneath continental and oceanic plates, and that melted material comes up to the surface. And on the way, it picks up a little bit of extra silica, so they're going to be silica-rich rocks, which makes them much less likely to flow, much more likely to be very explosively eruptive. They do have large symmetrical cones. They're more mountain-like, so less like perfectly symmetrical than the cinder cones, which look like very nice and smooth, but generally symmetrical. Built by layers of cinder and ash alternating with lava flows. They do produce lava much more often than like your cinder cone. Associated with explosive eruptions and abundant pyroclastic material. So when you think of like a volcano kind of going off, that's going to be the type of volcano that we're thinking of, a stratovolcano. Steep summits, gradually sloping flanks, a nice image. I don't know for sure, but I'm pretty sure that's Mount Fuji. Mount Fuji is definitely like the best looking volcano there is. It just really looks well in a picture. Nice, very pointy peak, levels out, and the sides slope down. Usually has snow on it. That'd be nice. I'd like to visit Mount Fuji one day. So, what are the characteristics of composite volcanoes? Alternating layers of ash and lava, very explosive eruptions, and a steep summit and gradually sloping flanks. So, what time is it? Are we almost? We leave at 27. We can go a little bit longer. We can get as far in as we can. We're doing all right. 38, yeah. So, volcanic hazards. What do we have to worry about when we're thinking about volcanoes, or if we live near a volcano? Roughly 70 volcanic eruptions are expected each year. That's going to be worldwide. One large volume eruption each decade. So it's not super often that we get like the big Mount St. Helens type eruption. I don't know if I mentioned this, but in the next semester, they have like case studies at the beginning of each chapter. When we get to the volcanic chapter, there's an Icelandic volcano that I will challenge you to be able to pronounce, and you will fail. We will all fail. Literally, like, I don't know that our muscles in our mouth palate like have the ability to create the sounds that are needed. Definitely our brains aren't up to the task, but it's a crazy word. So about 500 million people live near active volcanoes, which seems like interesting to say that like there's a lot of people that live near the ocean. It's like, okay, yeah, we use fishing, we use the ocean for transportation of goods. People living on the coast isn't that crazy. But 500 million people living near active volcanoes. Then you start to think of like Japan, where you can't live anywhere in Japan without being near an active volcano. Same thing with Hawaii, and the entire Pacific Northwest, Washington, Oregon. They're all around volcanoes there. So it's hard to avoid sometimes. Volcanic hazards, if you do live near a volcano, include obviously pyroclastic flows, the big explosive ash-filled cloud that we always see going up, but there's a big portion of it that goes down. So that's going to be what knocked down all those trees in the Mount St. Helens video, where you saw all the trees just flattened and leveled. That's what does that. Lahars are going to be mud flows. So if your volcano has a glacier at the top or a lot of snow and ice at the top, when the volcano erupts, all that's instantly going to melt. It's going to mix with ash, and it's going to flow downhill and clog up your rivers. Lahars are actually really crazy. We'll see a couple pictures of them later. Because they mix with the ash, and there's so much ash, when they stop moving, like once they get downhill and get to a flat area, very quickly they harden to like cement type consistency. And so if your like car gets caught in a lahar, you're not gonna like drive it out a couple days later. It's like lost to the volcano. The volcano took it. Lava flows, obviously. If you live close to a explosive volcano, those can be pretty dangerous. And like in like Hawaii, you have a warning time. The lava doesn't move super fast. Ash and volcanic gases are also a big deal. There was a volcanic eruption, and I think that's the Iceland one that we're going to talk about. Its ash went over the ocean and shut down a lot of air travel in Europe for like weeks and weeks and weeks, and it became a huge problem because you don't want the airplanes to try to fly through stuff like that. It's not going to be very good. I don't know. You think the person driving this Jeep right now is pretty worried? Yeah. Surprisingly, like I always saw this picture and I was like, well, they died. You're like seconds from death, but I think they survived. I think I saw other pictures of them basically further away from the cloud. But yeah, that's not a good position to be in. That ash cloud's going to get you. Okay. So we're going to talk about pyroclastic flow. And actually, I'm going to go ahead and stop here, and we'll pick up with pyroclastic flow tomorrow. We went through quite a bit. So let's see what we're going to cover tomorrow. We'll talk about pyroclastic flow, which is essentially, did I go too far? This is the pyroclastic flow. Ash and dust and little pieces of volcanic material all coming downhill at you. A lot of it goes up, but much of it is hot and super dense, and it flows down the hill and knocks down all the trees and covers up houses and does a lot of damage. So we'll talk about that. There's a before and after picture of a Mount Pelée eruption that kind of leveled the town. We'll talk about lahars, the mud flows, ash, sulfur dioxide, tsunamis, atmospheric cooling, all sorts of things. Volcanic hazards. We'll show you how caldera forms. Talk about fissure ruptures, volcanic necks, which are super cool. Intrusive igneous activities, so dikes and sills, discordant, concordant, plutons, batholiths, tabular features. Speaking of which, has everybody heard of the North Texas town called Rockwall? Rockwall, not surprisingly, is literally named after a rock wall. But that rock wall was not like a wall that people built out of rocks. It's an igneous intrusion. So it's like a thin crack in the earth that got filled up with like lava, magma, because it never got to the surface. And then eventually erosion happened, and they had this like wall of volcanic material. I don't know if they knew exactly what it was when the town was founded, but yeah, Rockwall is named after a rock wall, which happens to not be a rock wall, but a dike. And so pretty interesting. There's a section of it at UTA. The Giants Causeway. Is it the Giants Causeway? Is that what it's called? But anyways, that's a pretty cool place. Columnar joining, batholiths, stocks, lagaliths. Nice. And I think that is pretty close to it. Partial melting and the origin of magma. Yeah, we'll go through some complicated stuff. Not too bad, though. The Ring of Fire. Intraplate volcanism. All right, so we might be able to finish up tomorrow. We'll be kind of close. Oh, we already went through all that. All right, nice. So we'll end there for today. If you were being lazy, if not, forgive me. But for those of y'all being lazy and sleeping in at home today, you've drawn our ire. We resent you. Yeah, everybody have a nice day, and I will see y'all tomorrow.